Good morning, students. This is chapter number 30, nuclei, and today's topic is nuclear forces, nuclear fission, and nuclear fusion. Right? So we are starting this lecture by the stability of the nucleus. Now, stability of nucleus depends on three factors. Right? You have already seen the binding energy curve. The nuclei having higher binding energy per nucleon is more stable than the others. It means for the stability of nucleus, the binding energy per nucleon of the nuclei should be greater. Second factor is neutron-proton ratio. It means number of neutrons divided by number of protons. Students, you can see that in light nuclei, for example helium 2He4, there are 2 neutrons and 2 protons. It means the ratio is nearly 1:1, right? So helium is stable. But if we go for the heavy nucleus, the neutrons becomes higher than the protons. It means the ratio becomes greater than 1:1. It might be 1.5:1. So these nuclei becomes less stable due to neutron-proton ratio. So for stability, neutron-proton ratio should be appropriate. And third factor is configuration of the nucleus. Means if the nucleus having even configuration, it means they are most stable. For example, helium, there are 2 protons and 2 neutrons. It means the nucleus is even nucleus, even protons, even neutrons. If the nucleus having even odd or odd even, it means number of protons are even and number of neutrons are odd, or odd protons and even neutrons. So they becomes lesser stable, right? And the nuclei having odd configuration are least stable. It means odd number of protons and odd number of neutrons. For example, 3Li6. It means there are 3 protons, 3 neutrons. So this is odd nucleus. So even nucleus are more stable, even odd or odd even nucleus are lesser stable, and odd nuclei are least stable. Right? Now, nuclear forces. The nuclear forces in nucleus always act between proton-protons, proton-neutrons, and neutron-neutrons. It means all the nuclei having the force of attraction. For example, this is proton, this is neutron, then this is neutron, this is again proton. So this force may be between proton-neutron, neutron-neutron, or proton-proton. But this is the strongest force in the nature, right? So the nuclear forces are the forces that bind nucleus together. Since the forces are attractive forces, they are the forces between proton-proton, proton-neutron, or neutron-neutron, right? These are the strong attractive forces of totally different kind. Totally different kind. Means these forces are attractive forces. In fact, nuclear forces are the strongest force in the nature, right? So there is a particle that is called pi meson. Pi meson always play an important role for the production of nuclear forces. Now, some important features of nuclear forces. Number one, nuclear forces are short range strongest attractive forces in nature. Short range means these forces always act inside the nucleus, and the size of the nucleus is very small, 10 to the power minus 15 meter order. So it is short range force, and these are the strongest force in the nature. They are 100 times greater than the electrostatic force, right? Number 2, the nuclear forces between proton-proton, proton-neutron and neutron-neutron are approximately same. The nuclear forces are independent of electric charges. You can see here this force acting between proton-proton, proton-neutron and neutron-neutron. It means it is independent of charge. They do not obey inverse square law. Actually, this force is non-conservative force. So it do not obey inverse square law. Right? Always the conservative forces obey the inverse square law, but non-conservative forces do not obey inverse square law. They are spin dependent forces. It means they depends on the spin of the particles. In pair of proton, one is rotating anti-clockwise and another one is clockwise. So it depends on the spin of the particles. Particles means nucleons. Now this is the binding energy curve. The potential energy of nucleons versus separation. So potential energy between nucleons, potential energy of pair of nucleons and the separation between these nucleons. So this graph comes like this, right? This is the baseline. This one is the baseline. Below this line, this is negative potential energy, and above this is positive potential energy. Negative potential energy always occurs due to force of attraction. It means this is the result of attraction force, and this is the positive potential energy. It means it is at the cost of repulsive force. This x-axis shows the separation distance. As the nucleons come close together, the potential energy is decreasing, means negatively increasing, and at a certain point the negative potential energy becomes maximum. When the nucleons come further close together, the negative potential energy decreases and becomes zero. Now the positive potential energy takes place. It means for this sort of distance there is no force of attraction, no force of repulsion. Below this R0 equilibrium distance, there is a force of repulsion and there is force of attraction. It means if R is greater than R0, the force of attraction takes place. For R is less than R0, the potential energy increases rapidly. It means there is a strong repulsive nuclear force, right? But if the distance is greater than equilibrium distance, potential energy decreases to zero with increasing the R. It indicates that there is attractive nuclear forces. So if distance is R is greater than R0, it means there is a attractive nuclear force. And if distance is smaller than equilibrium distance R0, it means there is strong repulsive nuclear force, right? Now we come for the next topic, this is nuclear fission. Actually what happens in the third region, when the number of nucleons are greater, then the nucleus becomes less stable. And to achieve the stability, these nuclei try to decrease their mass number. And for that, the nuclear fission reaction takes place. It means a heavy nucleus splits into small fragments. This is called nuclear fission. Nuclear fission is defined as type of nuclear disintegration, right, in which a heavy nucleus splits into two light nuclei to comparable size, accompanied by the release of large amount of energy. When the heavy nucleus splits into light nuclei, so there will be the release of large amount of energy at the cost of mass defect. I have already told you that the nuclear reactions are always exothermic. The reason is that the mass of the product is always less than the mass of the reactants. So the energy produced at the cost of mass defect. Now this is an example. Uranium 235, a new slow neutron strike to the uranium 235. It becomes 92 uranium 236, and immediately it breaks into barium and krypton along with 3 neutrons. Now the mass of this product is less than mass of the reactants. So at the cost of this mass defect, a large amount of energy produces. This is called nuclear fission. So nuclear fission is the process in which a heavy nucleus splits into light nuclei along with liberation of energy. Now nuclear fusion. In light nuclei, the binding energy per nucleon is less. To achieve the stability, these nuclei fuse together and form a heavy nucleus. And in this process, a large amount of energy also produced at the cost of mass defect. This process is called nuclear fusion. Nuclear fusion is defined as a type of nuclear reaction in which two or more light nuclei merge into one another to form the heavier nucleus, accompanied by a release of large amount of energy. For example, 4,1H1, 4 hydrogen nuclei fuse together and form a helium nucleus, right? So there are 4 hydrogen nucleus fuse together, form helium along with large amount of energy. This energy is around 24 million electron volt. So this is the nuclear fusion, right? So this is all about of today's lecture, and this was the last lecture of the chapter number 13, nuclear. Thank you very much.